Greetings and welcome, friends. Mr. Waddy here with the Accelerated Geometry class. That's right, represent. So today we're talking about a new type of special segment. So far we've had 4. This will be special segment number 5 within a triangle. This segment, unlike the other ones, will not share concurrency amongst its counterparts. So there will be 3 versions of this special segment in any given triangle. But like I said, it will not have a single point of concurrency like the other ones did. And it is called a mid-segment. Mid-segment, Isaiah, that's right. And the mid-segment I'm going to construct by connecting the midpoints. Actually, watch how cool this is. So I just constructed the midpoints. And now I think with those connected, I can actually say just construct segments. Whoa. Bam! Look at that. Talk about time saver. Let's make this a nice color here. And so those orange segments are the mid segments of a triangle. Now notice they are not concurrent with one another, but they will intersect with each of the other. Isaiah, Jack, seriously guys, come on now. I don't understand. So they will connect with each of the other mid-segments. Question, comment?
Is that interior triangle formed by the
midpoints? Yeah, the mid-segments are constructed by connecting the midpoints of the triangle.
And is that a triangle?
Maybe one day we'll prove that. But yeah, that seems like an interesting case. Is this interior triangle similar to the others? I think we could prove that. What I want to show you, let's consider this mid-segment here. How do you think this compares to, say, this segment over here? Oh, all right. I heard parallelness first. Let's actually see if I can measure the slopes and look at the slopes of those. It threw me on a coordinate plane here. It's giving me decimal values of those slopes, but notice the slope of C to D and B to A are the same. All right, so it turns out that mid-segments will be parallel to the side of the triangle they don't touch. All right. How about in terms of lengths? How do you think those would compare? Yeah, I think so. Let's measure those lengths, and it looks like that's half. Do you guys remember how I could actually calculate the half of this number? How can I, in Geometer Sketchpad, tell it to just give me half?
You click on it.
You go to number and calculate. And then I say, hey, do this for me. Click on that and hit divide by 2. And notice here's the formula that I have. And the formula, no matter where I move this, 11.38 and 11.38, those are always going to be the same. So those are a couple of the properties of mid-segments. So a mid-segment of a triangle is a segment that connects the midpoints of 2 sides of the triangle. Every triangle has 3 mid-segments, which form, ooh, wow, guys, this might be, I mean, it has been like 8 years since I taught geometry, maybe 10, I don't remember. I don't think I remember that word, that term, mid-segment triangle. I feel like I either learned something new or I had to relearn it. That's fine, though. So it says the mid-segments of triangle ABC at the right are MP and MN and NP as shown, and that is the mid-segment triangle. Now, we discovered some properties just moments ago regarding parallelness, perilousness? No, that's not right. And halfness in terms of measurement, right, that they are proportionally smaller. Yes, careful with the shoe squeaks. So it says, example 1, in triangle JKL, show that mid-segment MN is parallel to JL. So MN and JL, how can I show or demonstrate parallelness in the coordinate plane? How do I demonstrate that? I like it. I like it. And what relationship do you expect regarding those slopes, Jack? They are, yeah, equal slopes will be parallel lines, assuming they are at least different lines. Yeah. So let's find slope 1. So I could use the slope formula, but tell you what, let's just read it right off the chart. Looks like that's going down 1 over 4 for the slope of that line, and the slope of the other line looks like it's going down 2 and over 8. Agreed? Which reduces to negative a quarter, down 1 over 4. So because these slopes are the same, therefore I could say MN is parallel. I feel like it's been a whole chapter since we talked about parallel. Maybe not. And JL are parallel segments because their slopes are the same. Let's see, then it asked me this, show that MN, the mid-segment, is half of the side of the triangle that it doesn't connect. How could I find those lengths? Distance. And in case you forgot, never gonna forget, distance formula. Oh, yeah. Distance formula is just a cousin of the Pythagorean theorem. It's going to be double distance formula here. Can I kind of read it off the graph? Here's a triangle that's a 1 by 4 by whatever, and here's a triangle that's a 2 by 8 by whatever. Once we talk about similarities of triangles, you guys could probably set up a proportion and be like, that's got to be half. But I'll do the double distance formula for you. So let's find MN is going to be, let's see, what are the coordinates for M? Do I have those? I don't done have them. Coordinates for M are what? -4, 3, and how about N? 0, 2. So the distance formula is going to be 0 minus a -4 all squared. Lots of parentheses there, and 2 minus 3. Distance formula, the order doesn't matter as much because you're just subtracting them and squaring them, and it will work out either way. 0 minus a -4 will be 4 squared, plus 2 minus 3 is -1 squared. Do not distribute a square root over addition. Don't just like cancel out those squares in that square root. Super illegal. Super illegal. 4 squared is 16 plus 1. Looks like the square root of 17, if I'm not mistaken, is the length of the MN. Right? Ooh, that was an ugly box right there. There we go. Let's find the length of JL. So the square root of 2 minus a -6 plus -1 minus a 1 squared. So I'm just plugging it in, right? It's not that bad. 2 minus a -6 is 8, so that's going to be 8 squared. Let's see, 8 squared plus -1 minus 1 is -2 all squared. That's going to be +4. So that's going to be 64 plus 4. That's the square root of 68. Now, I have a hunch that 68 is divisible by 4. I have a hunch. 4 goes into 64 16 times. It must go into 68 how many times? 17 times. I was rooting for that because I kind of wanted this to end up being, twice the length of the other one. So that's kind of what I'm rooting for. I don't know. Do you guys remember reducing radicals? Breaking it into the largest perfect square. The square root of 4 is 2. This is 17. Yeah, JL, notice, is exactly twice the length of MN. Lovely, lovely. Yeah. I mean, working in coordinates can be a lot of work. Let's see. So the mid-segment theorem is the theorem that tells us about this parallelness and this congruence. Let's see. Oh, this actually also. Well, no, I already knew that those would have been congruent to each other. Yeah, because those are midpoints. But it turns out that this entire segment over here is going to be twice as long as its parallel mid-segment. And if I connected these, that this right here would have been congruent to that and that if I connected it at the midpoint. But we didn't draw that. So good old mid-segment theorem, it tells you two things. How great is that? 2-for-1 deal. Let's see, we only got 3 examples today. We're on example 2 now. Yeah, not that bad, huh? No. Oh, there's 5? I'm completely wrong then. I don't know what I'm talking about. It says, oh dear, write a coordinate proof of the triangle midsegment theorem for one midsegment. All right, so let's do this fast. Let's find the slope of D to E. So notice they picked coordinates for B that were conveniently double, as well as this coordinate for C that was double. That was like smart thinking on their part when you're setting up a coordinate proof, Lauren. I'm sure you agree, right? Because if I find half of that, the coordinates for D are just going to be Q comma R. What are the coordinates for E going to be? Let's see, it's going to be R high. Actually, wait a minute. Yeah, how can I figure that out? Let's see. Wow. Guys, this is interesting. Wow. How could I find the x coordinate of E?
Yeah, it's not a true theorem.
Oh, wait, super easy. It's halfway between these two. So it's going to be halfway between 2P and 2Q. It's just going to be P plus Q. Here, let me do the midpoint formula.
Yeah.
So the midpoint, it would have been 2Q plus 2P all over 2, and it would have been 2R plus 0 all over 2. So the midpoint would have been, all those 2's cancel out, right, Jack? Right. And I'd have Q plus P, and here 2R plus 0 is 2R. Those 2's cancel out. I'd get R. So, yeah, I like that a lot. Wow. I like that. So here's the coordinates of E. What could I do? Let's find the slope of DE. Let's see, so DE slope, and what do I want that slope to be? I'm hoping it's 0, right? I'm hoping that it's 0. So let's see, so to find the slope, how do I do that? Y2 minus Y1 over X2 minus X1. Let's see. I'm running out of space here. R minus R is 0. Those Q's cancel out. 0 over P. Overpowered. Wow. O over P. Classic. The slope of DE is 0. Right? It doesn't even matter what the P is as long as P wasn't 0. So the slope of that is 0. You can also tell that the slope of OC is 0. Because those slopes are equal, then I would say that DE is parallel to OC. All right, so I just proved the parallelness. Now what do I need to prove? I need to prove the distance is half. You guys ready to do a distance formula using some crazy coordinates? All right, what's the distance of OC? It's 2P units long, right? So OC is 2P units. And now I'm trying to find DE. And that is going to equal the square root of, let's see, what were those coordinates? Should I rewrite those? It was what? QR And all right, so let's plug those in. So let's see, difference of the x's. So p plus q minus q all squared plus r minus r all squared. The q's cancel out, so that's p squared plus r minus r is 0. That's going to be the square root of p squared, which is just p. And notice that that is half of the other one. So it worked out. It done just worked out. Isn't that lovely? Let's get to example 3. Like I said, we'll at least get that far. Won't be that bad. It's almost like they're looking for ways to make these more challenging by doing the coordinate stuff. But then like the actual application of them isn't that bad. Okay, so here we go. Triangles are used for strength in roof trusses. No way! Guys, our friends in the video were doing roof trusses. What? Wow. It says in the diagram, UV and VW are mid-segments. So UV and that I just highlighted VW. UV and VW are mid-segments of this larger outside triangle. It says find UV and RS. So let's see, what do you think UV is going to be? It's going to be half of RT, which is 90. So that's just 45. Right? You guys see that, right? It's going to be half of this. And let's see, then they ask me find RS. RS is this value. RS is going to equal twice the length of VW. So it looks like RS is going to be 114. Right? Like the actual application of these is not that hard. It's just like doubling stuff or using parallelness. Yeah. Let's see. You guys think I can do example 4 in 2 minutes? I think I can. I take that challenge, friends. Oh yeah, you challenged me. Look at this is like a great little kaleidoscope. Kaleidoscope.
30 seconds. Go.
All right, here we go. In the kaleidoscope image, AE. Let's see if I can label these. What's a good color? There's too many colors. I guess yellow. AE is congruent to BE. I'm just going to verbally do this. And AD is congruent to CD. All right, so that means D is a midpoint, E is a midpoint. That means DE is a midsegment by definition of midsegment. It says show that CB is parallel. CB is parallel to DE. Why is CB parallel to DE? By the mid-segment theorem. Right? Bam. Nailed it. All right. Well, thank you for watching, Internet friends.